Hello class, in this lesson we're going to learn about the difference between continuity and differentiability. So first of all, I'm going to look at what does it mean to be differentiable and continuous. In order for a function to be differentiable, or in other words, the derivative exists at a point, then it must be continuous at that point. So for it to be continuous, at least it has to at least be differentiable. And if a function is not continuous, then by default it cannot be differentiable. Hopefully that makes sense. State the intervals on which the function is continuous, then state the intervals in which the function is differentiable. So we're going to look at three graphs here, 1, 2, and 3. And just by looking at these, we're going to talk about are they continuous or are they differentiable, and where are they continuous and differentiable. Looking at the first one, you see two lines. Okay, this is the shape is called a hyperbola. And the problem is that it's not continuous somewhere. There's a gap right here. And you notice that that gap exists at x equals -3. So this, at the bottom, when I say this is continuous, I'm going to say it's continuous everywhere except, this is continuous except x equals, or it's continuous everywhere except at x equals -3. Differentiable means, the limit matches from the left and the right, and I could take the derivative at that, or it matches the value at that point. It is also continuous everywhere, or differentiable everywhere except at x equals -3. I can't take the derivative at x. Like, there's no derivative here because the left and the right and the actual value do not line up. When I look at the second graph, it's a graph of a parabola. It looks like it's continuous everywhere, but if you look very closely, it's not continuous at this one point right here. So that occurs at x equals 2. So this graph is continuous everywhere except at x equals 2. Now, is it differentiable everywhere? Well, it looks like it's differentiable. Everything matches up left and right. Also not differentiable at this point. The limit exists at this point because the left and the right match, but see how there's missing a value here? So it's also, you also cannot take the derivative at this point. So it's differentiable everywhere except at 2. Now let's look at this one. This one's going to be a little bit different. This is the graph of a square root function. Now, where is this continuous? Well, it's continuous everywhere, for everywhere except for greater than or equal to 2. Right? It's one continuous line, including 2 because I have a closed dot, and everywhere I have a continuous function. So this is continuous everywhere when x is greater than or equal to -2. But it is not differentiable at -2. And the reason why you can't take the derivative at -2 is, do you see how there's nothing coming from the left? Right? For something to be a derivative, it has to have a matching left, matching right, and the exact same value. But here at -2, there's no line, there's nothing coming from the left. So this graph is differentiable everywhere for x is greater than -2, but not including -2 because there's no left or right. So that's a basic definition of it. We did these in class, and just in case you forgot, you also have instances where it is continuous but not differentiable. Here it's continuous, this line doesn't break, so it's continuous on everywhere. Let me just write this sloppy. But it's not differentiable here. I have a sharp line, and maybe you didn't understand it in class, but it's not, I can't take the derivative, or I can't find the slope at this point because this slope changes like really drastically. It's like a sharp turn almost. So I cannot take the derivative at very, very, very sharp points because I can't figure out what the slope is at that point. The slope here is undefined. So differentiable everywhere except x equals 0. Now, on this bottom one, same thing. I have a sharp corner here at 3. There's no gaps or anything. Continuous everywhere. And differentiable everywhere except for x equals 3. And the last one is that special case I was telling you about. Here, if I zoom in closer at -2, I have a straight line. The slope here is actually infinity. And you can't take the slope of that, or it's sort of undefined. Infinity is undefined. It's an S curve that doesn't break or gap, so it's also continuous everywhere. And it's differentiable everywhere except at -2 because I have that straight line. Now that you know how to do that, let's go to one that is algebraic. So here's the one that we also did in class. It says I have a vertical tangent line at -3 and a tangent line at -7. determine the x values where the function is continuous but not differentiable. It's not differentiable here because I have a straight line or a slope of infinity. So it's not differentiable at -3 because I have an infinite slope. And it's also not differentiable here, x equals 1, because I have a sharp corner. And that's all you have to do. And now that you know how to do that, and again, this is what we did in class, I'm going really quickly. You should be able to do this also algebraically. This question says, here's a piecewise function. Is it continuous at 4? For it to be continuous at 4, I should be able to plug in 4 in the top and the bottom. You might remember this from the last lesson, in the previous unit. And if I get the exact same number, it's continuous because they're connected. They have the exact same value. If I plug in 4 into this one, I'm going to get 16 minus 4, and I'm going to get 12. Okay. If I plug 4 into this one, I'm going to get 20 minus 8. I will also get 12. So since they match top and bottom, when I plug in 4, it is continuous. The next question says, is this differentiable? Can I take the derivative of 4? Well, remember, if the derivative exists, I should be able to take the derivative from both sides and have the exact same slope, and then I'll have the differentiable. So if I take the derivative of this first function, this x squared minus x, I get a derivative of 2x. And then when I plug in 4, I get 8. So that tells me from the left side, my derivative and my slope is 8. From the right side, if I take the derivative, I get 5. Okay, and there's nowhere to plug in, so my slope is 5. So do you see how these slopes here and here do not match from the left and right? So this is not differentiable. And if you are confused about what that means or what that looks like, this is the exact meaning of a sharp corner. It's a slope of 8, and all of a sudden it changes to a slope of 5. It changes slope almost instantaneously. And then the last thing, the last page, we did these, or this page right here where it says another piecewise function. This I'm going to cancel out, so you don't need to know that. And this one we did in class, and just to review again, is it differentiable at -4? At -4, I have a slope of 0. A slope of 0 is still a differentiable, so yes, it is differentiable. Okay, has a slope of 0. But at -2, is it differentiable? No, because I have a sharp corner. So that is the difference between continuity and differentiability. Hopefully you understand. We'll practice in class. And yeah, I'll see you guys in class. Take care.